They were never supposed to be there. For decades, astronomers believed they understood the opening chapters of cosmic history. The story seemed straightforward. The universe was born in a violent flash of energy nearly 13.8 billion years ago. In the beginning, there were no stars, no galaxies, no planets, and certainly no observers looking back through time. There was only an expanding sea of particles slowly cooling as space itself stretched outward. Then came darkness. For hundreds of millions of years, the young universe drifted through what astronomers call the cosmic dark ages. Hydrogen gas filled space like an endless fog. Light existed, but there were no stars yet to illuminate the vast emptiness. Gravity was quietly gathering matter together, preparing the stage for the first generation of stars. According to every major model, the first galaxies should have been small, fragile, primitive. They should have resembled cosmic seedlings just beginning their journey. And then the James Webb Space Telescope opened its golden eye. Almost immediately, something strange appeared. At first, they looked insignificant. Tiny reddish smudges hidden within the deepest images ever captured. To an ordinary observer, they might have seemed like nothing more than faint dots scattered across a black background. But astronomers quickly realized they were looking at objects whose light had traveled for more than 13 billion years before finally reaching Earth. These galaxies were ancient. Not ancient by today's standards, ancient by the standards of the early universe itself. The light showed that many of them existed only 500 to 700 million years after the Big Bang. That alone was not shocking. Scientists expected galaxies to exist during that era. What shocked them was what those galaxies looked like. They were enormous. Some appeared to contain hundreds of billions of stars. Others seemed comparable in mass to our own Milky Way galaxy. Even more unsettling was the color of the stars they contained. Rather than appearing bright blue and youthful, many looked red and mature. To understand why this is so surprising, imagine walking into a nursery and finding fully grown adults sitting in cribs. That is essentially what astronomers were seeing. These galaxies appeared far too developed for their age. The universe should not have had enough time to build structures of that scale. Stars need time to form. Galaxies need time to merge. Matter needs time to collapse under gravity. Every step requires hundreds of millions, sometimes billions of years. And yet somehow, these giant galaxies seem to have skipped the entire process. The discovery spread rapidly through the scientific community. Some researchers questioned the measurements. Others questioned the models. A few quietly wondered whether something fundamental about our understanding of cosmic evolution might be missing. The situation became even stranger when scientists compared these observations with decades of data collected by the Hubble Space Telescope. Hubble had spent years searching for the earliest galaxies. Most of what it found matched expectations. Young galaxies appeared small, irregular, and intensely blue. They looked exactly like cosmic structures in the process of assembling themselves. Webb was seeing something completely different. It was as though two historians had opened the same ancient book and discovered entirely different first chapters. Of course, extraordinary claims require extraordinary evidence. Astronomers immediately began searching for alternative explanations. Perhaps these galaxies only appeared massive because of unusual concentrations of bright stars. Perhaps early stars produced light differently than modern stars. Perhaps the galaxies were actually closer than they appeared, and their distances had been miscalculated. Each possibility offered a temporary refuge from a more uncomfortable conclusion. Because if the measurements were correct, then something about the early universe worked differently than scientists thought. And that possibility is both terrifying and exciting. science advances by discovering where it is wrong. Every major breakthrough begins with an observation that refuses to fit inside existing theories. The expansion of the universe, black holes, dark matter, dark energy. None of these ideas emerged because scientists were searching for them. They appeared because nature revealed something unexpected. Now, once again, the universe may be presenting another mystery. The deeper Webb looks, the more ancient surprises seem to emerge from the darkness. Every image captured by the telescope is more than a photograph. It is a message from another time. The photons entering Webb's mirrors tonight may have begun their journey before Earth existed, before the Sun formed, before our solar system was anything more than atoms drifting through interstellar space. When we observe distant galaxies, we are not merely looking far away. We are looking backward. Every additional billion light years becomes another billion years into the past. The telescope is functioning as a time machine built not from science fiction, but from physics itself. And as Webb pushes deeper into cosmic history, the universe is beginning to reveal chapters that no one expected to read. Perhaps these giant early galaxies are only the beginning. Perhaps they are clues pointing toward hidden processes that shaped the young cosmos. Or perhaps they are warning signs that some of our most trusted models are incomplete. For now, nobody knows. What scientists do know is that the James Webb Space Telescope has opened a new era of exploration, an era in which the oldest light in existence can finally be examined with unprecedented clarity. And if the first discoveries are any indication, the universe may be far stranger than anyone imagined. Because before we can understand why these impossible galaxies exist, we first need to understand the machine that found them. And that machine may be one of the greatest engineering achievements humanity has ever built. Long before the James Webb Space Telescope began rewriting astronomy textbooks, it existed only as an impossible dream. Scientists knew that if they wanted to witness the birth of the first galaxies, they would need something far more powerful than any telescope humanity had ever constructed. The challenge was almost absurd. The earliest galaxies are unimaginably distant. Their light has spent more than 13 billion years crossing the expanding universe before finally reaching us. During that journey, something strange happens. As space expands, it stretches the light itself. Colors that originally left those galaxies as visible light become stretched into infrared wavelengths. By the time the ancient photons arrive here, they have effectively changed their identity. To see the beginning of cosmic history, astronomers would need a telescope capable of seeing infrared light with unprecedented sensitivity. Not merely a little better than previous observatories, but dramatically better. The result would become the most ambitious space telescope ever attempted. From the beginning, the project seemed cursed by complexity. Budgets grew, deadlines slipped, engineers faced problem after problem. What was originally expected to cost only a few $1 billion eventually surpassed $10 billion. Critics questioned whether the telescope would ever launch. Some wondered if it would become one of the greatest scientific failures in history. Yet the vision remained alive because the reward was extraordinary. If successful, Webb would allow humanity to look deeper into time than ever before. It would become a machine designed to study the first generation of stars, the earliest galaxies, and perhaps even the conditions that eventually allowed life itself to emerge. The telescope that finally emerged from decades of development barely resembles traditional telescopes. Most people imagine telescopes as long tubes with lenses pointing toward the sky. Webb looks more like a gigantic golden flower floating above a silver kite. Fully deployed, it spans roughly the size of a tennis court. Its primary mirror stretches more than 21 feet across, making it vastly larger than Hubble's famous mirror. Yet despite its enormous size, Webb's mirrors are astonishingly lightweight. Engineers removed over 90% of the original mass during manufacturing, creating mirror segments that are both incredibly strong and remarkably light. The golden appearance of Webb has become iconic, but surprisingly, the mirrors are not made of gold. Their structure consists primarily of beryllium, a lightweight metal chosen because it remains stable even under extreme temperature changes. The gold itself exists only as an ultra-thin coating. In total, the entire telescope contains less than 2 ounces of gold. If melted down, it would form a ball roughly the size of a golf ball. Yet that microscopic coating dramatically improves the mirror's ability to reflect infrared light, allowing Webb to collect faint signals that have traveled across nearly the entire history of the universe. Collecting ancient light is only part of the challenge. The telescope must also remain unimaginably cold. Infrared light is essentially heat radiation. Everything with a temperature emits it. If Webb became warm, its own heat would overwhelm the faint infrared signals arriving from distant galaxies. The telescope would effectively blind itself. To prevent this, engineers designed one of the most extraordinary components ever sent into space: a massive 5-layer sunshield, stretching beneath the mirror like an enormous silver sail. This structure constantly blocks heat from the sun, Earth, and Moon. On one side of the telescope, temperatures can exceed 200 degrees Fahrenheit. On the other side, the instruments remain near minus 370 degrees Fahrenheit. This dramatic difference allows Webb to operate in conditions cold enough to detect some of the faintest infrared signals imaginable. Even launching the telescope required extraordinary planning. Webb was folded like a giant piece of cosmic origami inside its rocket. Once in space, hundreds of deployment steps had to occur perfectly. Unlike Hubble, which orbits relatively close to Earth and could be repaired by astronauts, Webb was heading to a location nearly 1 million miles away. Any major deployment failure would likely end the mission forever. Engineers spent years preparing for every possible scenario because there would be no second chance. As the telescope unfolded itself piece by piece, the world watched anxiously. Mirrors extended, antennas deployed. The gigantic sunshield stretched outward. Every successful step felt like a small miracle. The telescope was slowly transforming from a folded machine into the most powerful observatory ever built. Yet even after deployment, another challenge remained. The 18 mirror segments had to behave as though they were a single mirror. Tiny motors adjusted each segment with astonishing precision. The alignment tolerances were measured in fractions of the width of a human hair. Gradually, over weeks and months, the mirrors synchronized into a unified optical surface, capable of focusing ancient starlight with breathtaking clarity. Then came another remarkable detail. Webb does not orbit Earth like Hubble. Instead, it resides near a special location known as the second Lagrange point, or L2. Located roughly 1 million miles beyond Earth, this gravitational balance point allows the telescope to maintain a relatively stable position while orbiting the Sun alongside our planet. Here, Earth and the Sun remain on the same side of the telescope, making it easier for the sunshield to protect the observatory from unwanted heat. The location is so ideal that many future observatories may eventually join Webb there. When the first images finally arrived, they exceeded even the most optimistic expectations. Scientists anticipated years of careful observation before major discoveries would emerge. Instead, groundbreaking results appeared almost immediately. Ancient galaxies seemed larger than expected. Stellar nurseries revealed details never seen before. Exoplanet atmospheres began yielding chemical secrets. The telescope was not merely performing well, It was transforming entire fields of astronomy within months. What makes Webb truly extraordinary is not simply its size or technology, it is the unique combination of engineering and purpose. Every mirror, every detector, every cooling system exists for one reason: to collect ancient photons, tiny particles of light that began their journey billions of years ago. Some were emitted before the Milky Way fully formed. Some left their galaxies when the universe was only a few 100 million years old. Those photons crossed unimaginable distances through expanding space before finally ending their journey inside Webb's detectors. And as those ancient signals arrive, they tell stories. Stories of galaxies being born, stories of stars igniting for the first time, stories of black holes growing in the darkness, stories from an era so distant that it almost feels disconnected from our own existence. Yet every atom in our bodies ultimately traces its history back to those early cosmic events. The first stars forged the heavier elements that would later become planets, oceans, mountains, and living creatures. When Webb observes the dawn of the universe, it is not simply studying distant objects. It is exploring the earliest chapters of our own story. And as the telescope continues to gaze deeper into space and further into time, it begins uncovering mysteries even stranger than the giant galaxies that first captured the world's attention. Among them is a tiny ancient object whose light may come from only 300 million years after the birth of the universe itself. A galaxy so old, so distant, and so mysterious that it may offer our clearest glimpse yet into the moment when cosmic darkness first gave way to light. By the time the James Webb Space Telescope finished unfolding its mirrors and began sending back its first observations, astronomers were eager to test one of the oldest ideas in modern science. If Webb could truly see farther than any telescope before it, then perhaps it could answer a question humanity has been asking for generations. What did the universe look like when the darkness finally ended? Because despite everything we know about galaxies, stars, and planets, there is a chapter in cosmic history that remains strangely mysterious. A chapter that no human has ever witnessed. A chapter that unfolded long before the Milky Way existed and billions of years before Earth formed around our young sun. To understand it, we need to travel backward, far beyond the age of dinosaurs, far beyond the formation of our planet, far beyond the birth of the solar system, all the way back to a time when the universe itself was still an infant. The Big Bang did not immediately fill space with stars and galaxies. In fact, after the initial explosion of energy, the cosmos entered a surprisingly dark phase. The universe expanded, temperatures dropped, hydrogen and helium atoms formed, yet there were still no stars shining in the sky, no planets orbiting distant suns, no galaxies illuminating the darkness. For hundreds of millions of years, the universe was essentially a vast ocean of invisible gas stretching in every direction. Astronomers call this period the Cosmic Dark Ages. It is one of the least understood eras in the history of existence. Gravity was quietly at work during this time. Tiny differences in density left behind by the Big Bang itself slowly grew stronger. Regions containing slightly more matter began attracting additional matter. Massive clouds of hydrogen drifted together. Temperatures increased. Pressures rose. The cosmos was preparing for something extraordinary. Then, somewhere in that darkness, the first stars ignited. No one knows exactly what they looked like. No telescope had ever been powerful enough to observe them directly. Before Webb, scientists could only build theoretical models and simulations. They believed the first stars may have been vastly different from those we see today. Modern stars contain elements such as oxygen, carbon, silicon, magnesium, and iron. The first stars had none of these ingredients. They formed almost entirely from hydrogen and helium, the simplest elements in existence. Because of this, many researchers suspect they grew to enormous sizes. Some may have been hundreds of times more massive than our Sun. They burned hotter, lived shorter lives, and died in explosions so powerful they transformed the surrounding universe. Those explosions changed everything. Before the first stars existed, the universe contained very few chemical ingredients. After they died, space became enriched with new elements forged inside their cores: carbon, oxygen, iron, calcium, the building blocks of planets, the building blocks of life. Every breath you take contains atoms manufactured inside ancient stars. The calcium in your bones, the iron in your blood, the oxygen flowing through your lungs. All of it originated in stellar furnaces that lived and died billions of years ago. In a very real sense, the story of humanity began inside stars. And this is precisely why Webb's search for the earliest galaxies is so important. It is not simply about finding distant objects. It is about tracing our own origins. The farther Webb looks, the closer it comes to the moment when the universe first became capable of producing everything that would eventually follow. This is where the discoveries become especially fascinating. Scientists expected Webb to find primitive galaxies, small collections of stars just beginning to emerge from cosmic darkness. Instead, many of the galaxies appearing in the telescope's deepest observations seem unexpectedly mature. Some contain far more stars than expected. Others appear surprisingly organized. Several look as though they have already undergone significant evolution, despite existing only a few 100 million years after the Big Bang. The deeper Webb peers into the early universe, the more it encounters objects that seem to have grown up too quickly. It is almost as though cosmic history accelerated during its earliest chapters. Astronomers are now faced with a difficult possibility. Perhaps their models are incomplete. Perhaps stars formed faster than expected. Perhaps galaxies assembled themselves more efficiently. Or perhaps some ingredient of the early universe remains hidden from us. Nobody knows yet. And that uncertainty is exactly what makes this era of discovery so exciting. For decades, cosmology operated largely within a framework that seemed increasingly secure. Webb has begun testing that framework in ways never before possible. Every new observation provides another clue. Every new galaxy adds another piece to a puzzle that stretches back nearly 14 billion years. What makes the situation even more remarkable is that Webb is not merely observing ancient light. It is observing light that has been transformed by the expansion of space itself. As the universe expands, light traveling through it becomes stretched. Wavelengths grow longer. Colors shift toward the red end of the spectrum. The oldest galaxies therefore become almost invisible to ordinary telescopes because their light has been stretched into infrared wavelengths. This is exactly why Webb was built. Its instruments were designed specifically to capture these faint infrared signals. Ancient photons that left their galaxies billions of years ago are finally arriving at the telescope. They carry information from an era that was previously inaccessible. Each photon is a messenger from the distant past, a survivor of nearly 14 billion years of cosmic history. And now, for the first time, humanity has built an instrument capable of reading those messages with extraordinary clarity. Yet perhaps the most profound realization emerging from Webb's observations is how connected everything truly is. The galaxies appearing in these images are not separate from us. They are our ancestors. The stars inside them forged the elements that later became planets. Those planets eventually formed new generations of stars. Around one of those stars, in a quiet spiral arm of the Milky Way, a small rocky world emerged, and on that world, billions of years later, living beings evolved who would eventually build a telescope capable of looking back toward the beginning. The universe has spent nearly 14 billion years telling a single story. Webb is simply allowing us to read its earliest pages. And as those pages become clearer, another question naturally emerges. If the first stars created the ingredients for planets, what kinds of worlds eventually formed from that cosmic inheritance? As Webb continued its mission, it began turning its attention from the birth of stars to the strange worlds orbiting them. And what it found there was every bit as surprising as the impossible galaxies that started this journey. The first stars did more than illuminate the darkness. They transformed the universe itself. Before they existed, the cosmos was astonishingly simple. Hydrogen and helium dominated nearly everything. There were no rocky planets, no oceans, no mountains, no chemistry complex enough to support life. The universe was vast, but in many ways it was unfinished. Then the first generations of stars lived and died. Inside their cores, unimaginable temperatures forged new elements: carbon, oxygen, silicon, magnesium, calcium, iron, elements that would later become planets, atmospheres, and living organisms. When those stars exploded, they scattered their contents across space, enriching the cosmos with the raw materials for future worlds. Every planet that exists today is built from the ashes of ancient stars. Earth is, Mars is, Jupiter is, and every exoplanet orbiting distant suns is as well. So as the James Webb Space Telescope continued looking outward, it wasn't just studying galaxies anymore. It was following the consequences of those first stellar generations. It was tracing the chain of events that eventually produced entire planetary systems. And what it found was extraordinary. For decades, exoplanets existed mostly as numbers in scientific databases. Astronomers knew they were there because of tiny changes in starlight. A slight dip in brightness would reveal a planet passing in front of its star. Small wobbles in stellar motion hinted at unseen worlds tugging on their suns through gravity. Thousands of exoplanets had been discovered this way, yet most remained little more than distant statistics. Webb changed that. For the first time, astronomers could begin studying some of these worlds in remarkable detail. Not by traveling there, not by taking conventional photographs, but by analyzing the faint traces of light passing through their atmospheres. When a planet crosses in front of its star, a tiny portion of the starlight filters through the planet's atmosphere before reaching our telescopes. Different gases absorb different wavelengths of light. By carefully studying which wavelengths disappear, scientists can identify the chemical ingredients present in alien skies. It is an astonishing achievement. Imagine standing thousands of miles away and determining the composition of someone's breath. Now imagine doing it across dozens or hundreds of light years. That is essentially what Webb is capable of. One of its early successes came with a world known as HS 475b, located roughly 41 light-years from Earth. This planet is remarkably similar in size to our own world. While it is unlikely to be a second Earth, its discovery demonstrated something important. Webb could successfully study planets roughly the size of our home planet. This may sound like a technical milestone, but its implications are profound. For generations, one of humanity's greatest questions has remained unanswered. Are we alone? To answer that question, we first need to identify worlds capable of supporting life. That requires understanding their atmospheres, their temperatures, their chemistry. Webb is providing the tools necessary to begin that search. Yet while some discoveries inspire thoughts of future habitability, others reveal environments so strange that they challenge our imagination. One of the most fascinating examples is an object called VHS 1256b. At first glance, it appears to be a planet. Then again, it also resembles a star. In reality, it exists somewhere in between. Astronomers classify it as a brown dwarf, a category often described as failed stars. These objects are too massive to be ordinary planets, yet not massive enough to sustain the hydrogen fusion that powers true stars. They occupy a strange middle ground, neither planet nor star, neither fully one thing nor the other. VHS 1256b is particularly unusual. It possesses nearly 20 times the mass of Jupiter and orbits a pair of red dwarf stars at an enormous distance. One complete orbit takes thousands of years. For years, astronomers struggled to understand its strange reddish appearance. Only after Webb began studying it did the explanation become clear. The atmosphere of this bizarre world is filled with clouds, but not the kind we know on Earth. There is no water vapor drifting through these alien skies. Instead, the clouds appear to consist of microscopic particles of silicate minerals. In simpler terms, sand. Imagine standing beneath a sky where fine grains of mineral dust float through the atmosphere like clouds. Imagine sunsets glowing through drifting layers of airborne quartz. Imagine weather systems composed not of rain and snow, but of mineral particles suspended in superheated air. This is not science fiction. This is a real object observed by Webb. And the atmosphere is anything but calm. Researchers believe violent storms constantly churn through its skies. Layers of methane, water vapor, carbon monoxide, and silicate particles interact in ways unlike anything found in our solar system. The atmosphere appears dynamic, chaotic, and ever-changing, a world suspended between planetary and stellar existence. A reminder that nature often produces things far stranger than human imagination. The discovery is important for another reason. For years, scientists predicted that exotic mineral clouds should exist on certain worlds. Yet predictions are one thing, evidence is another. Webb provided that evidence. For the first time, astronomers could directly observe the signatures of these alien cloud systems. And as exciting as that may be, it also hints at something larger. Every time scientists develop a new instrument capable of seeing the universe more clearly, nature responds by revealing something unexpected. Every generation believes it has a reasonable understanding of reality. Then a better telescope arrives, and reality becomes stranger. The same process happened with Galileo's telescope. It happened with Hubble. And now it is happening again with Webb. The universe is proving itself more creative than our theories, more diverse than our expectations, more complex than our assumptions. The farther we look, the less ordinary existence appears. Yet even these strange worlds are only individual pieces within a much larger cosmic ecosystem. Planets do not emerge from nothing. They form inside vast stellar nurseries where gas and dust slowly gather around newborn stars. To truly understand where these alien worlds come from, we must move beyond the planets themselves and travel to the places where entire solar systems are born. Fortunately, that is another area where the James Webb Space Telescope has begun revealing details never before seen. And what awaits inside those stellar nurseries may be even more beautiful than the worlds they eventually create. Every strange planet, every distant moon, every asteroid drifting through the darkness shares a common origin story. Before there were worlds, there were clouds, enormous clouds, clouds so vast that entire solar systems could disappear inside them unnoticed. Clouds of hydrogen, dust, ice, and the recycled remains of stars that had lived and died billions of years earlier. For most of human history, these regions appeared as little more than faint smudges in the night sky. Beautiful, certainly. Mysterious, absolutely. But their true nature remained hidden behind thick curtains of gas and dust. The James Webb Space Telescope was built specifically to see through those curtains, and when it did, some of the universe's most secretive regions suddenly came alive. One of the most spectacular examples is the Carina Nebula, a colossal stellar nursery located roughly 7,500 light-years from Earth. Earlier telescopes had shown portions of this immense cloud before, but Webb revealed something different. It revealed a landscape, not a landscape of mountains and valleys, but a landscape sculpted by gravity, radiation, and time itself. Towering walls of gas stretch across space like cosmic cliffs illuminated by the light of newborn stars. Dense clouds twist and fold into one another. Brilliant points of light emerge from darkness like campfires scattered across a distant wilderness. The scene is so detailed that it almost feels impossible. Yet every glowing structure, every ripple, every luminous edge represents real physical processes unfolding across hundreds of light years. For a moment, it feels less like looking through a telescope and more like looking through a window. What makes these regions particularly fascinating is that they allow us to witness the earliest stages of star formation. Stars do not simply appear. They begin as tiny fluctuations inside enormous molecular clouds. Gravity slowly pulls gas inward. The material becomes denser. Temperatures rise. Eventually, the collapsing cloud forms a hot central core. If enough mass accumulates, nuclear fusion ignites. A star is born. The process sounds simple when described in a few sentences. In reality, it unfolds across millions of years. And it is astonishingly violent. As newborn stars ignite, they begin blasting their surroundings with intense radiation and stellar winds. Powerful jets erupt from their poles. Shock waves tear through nearby clouds. Entire regions become battlefields between gravity attempting to build structures and radiation attempting to destroy them. This cosmic struggle creates some of the most beautiful sights in the universe. Webb's observations have revealed jets of material shooting from infant stars like enormous interstellar fountains. These streams can extend for trillions of miles, carving paths through surrounding clouds. The telescope has also detected protoplanetary disks, vast rotating structures of gas and dust surrounding young stars. These disks are where planets begin. If the stars we discussed in the previous chapter were the furnaces that created the ingredients of existence, these disks are the workshops where those ingredients are assembled into entirely new worlds. Tiny grains collide. Dust becomes pebbles. Pebbles become rocks. Rocks become planetesimals. And over millions of years, gravity assembles those fragments into planets. Some become gas giants larger than Jupiter. Some remain frozen worlds on the outskirts of their systems. Others may eventually develop oceans, atmospheres, and conditions suitable for life. Right now, somewhere in the Milky Way, countless Earth-like worlds may be forming inside these stellar nurseries, and Webb is allowing us to watch the process unfold. One of the most breathtaking examples comes from the Tarantula Nebula, the largest star-forming region in our local cosmic neighborhood. Located inside the Large Magellanic Cloud, approximately 160,000 light-years away, this immense structure contains some of the most active stellar nurseries known to science. Earlier observations hinted at its complexity. Webb revealed an entirely different level of detail. Thousands of previously hidden stars suddenly appeared. Regions that once seemed dark turned out to be crowded with newborn suns. Dense clouds glowed with intricate structures. Infant stars emerged from cocoons of dust. The telescope even detected protostars actively gathering material from their surroundings. In other words, Webb caught stars in the act of becoming stars. It is difficult to overstate how remarkable this is. For most of human history, stars seemed eternal. Ancient civilizations viewed them as fixed points in the heavens. Even after astronomy advanced, the timescales involved remained so immense that stellar evolution often felt abstract. Webb changes that perception. For the first time, we can clearly observe the environments where stars are actively forming and planetary systems are taking shape. We are witnessing chapters of cosmic history that eventually lead to the emergence of worlds, including worlds like our own. In fact, if someone had observed the solar system roughly 4.6 billion years ago, they might have seen something surprisingly similar. Our Sun was once surrounded by a rotating disk of gas and dust. Jupiter did not exist yet. Earth did not exist yet. Neither did the Moon. Everything that would eventually become our planet was scattered throughout a chaotic cloud orbiting a newborn star. The mountains, oceans, continents, and even the atoms inside your body were once microscopic particles drifting through that disk. There is something profoundly humbling about that realization. The universe builds extraordinary things from simple beginnings. Stars emerge from clouds, planets emerge from dust, life emerges from chemistry, and consciousness emerges from life. A chain of events stretching across billions of years connects the stellar nurseries Webb observes today with the existence of every human being listening to this story. Yet these nurseries are not the end of the journey. Far from it. The stars being born inside these clouds will eventually age. Some will swell into red giants. Others will explode as supernovae. A few will collapse into objects so extreme that they warp the fabric of space itself. And among those remnants lie some of the most mysterious structures in the universe. Objects whose gravity is so powerful that not even light can escape. As Webb continues exploring cosmic evolution, it inevitably encounters these giants lurking in the darkness. And some of them appear far older, far larger, and far more difficult to explain than anyone expected. The stars forming inside places like the Carina and Tarantula nebulas represent beginnings. But every beginning eventually leads to an ending. Some stars will live for billions of years, quietly converting hydrogen into heavier elements. Others will burn through their fuel with astonishing speed, shining brighter, growing larger, and dying younger. The most massive among them will experience deaths so violent that they reshape entire regions of space. And from those deaths emerge some of the strangest objects in existence. Black holes. For decades, black holes occupied a strange place in science. They were accepted mathematically long before they were accepted emotionally. The equations said they should exist. Observations increasingly suggested they did. Yet there remained something deeply unsettling about the idea itself, a region of space where gravity becomes so powerful that not even light can escape, a place where our understanding of physics begins to fracture, a boundary beyond which information appears to vanish. The concept feels less like astronomy and more like mythology. And yet black holes are real. Not only are they real, they appear to be everywhere. Small black holes form when massive stars collapse at the end of their lives. But these are not the objects that have captured astronomers' attention in recent years. What truly fascinates researchers are the monsters, the supermassive black holes. These cosmic giants sit at the centers of galaxies. The one lurking at the heart of the Milky Way contains roughly 4 million times the mass of our Sun. That sounds enormous until you realize it is relatively modest compared to some of the behemoths Webb has begun investigating. One of the telescope's observations revealed evidence of a supermassive black hole weighing approximately 9 billion solar masses. 9 billion. To appreciate that number, imagine compressing 9 billion suns into a region smaller than our solar system. The result would be a gravitational monster capable of controlling the motion of entire galaxies. The mystery isn't merely that such black holes exist. The mystery is how they grew so quickly. This problem echoes the same puzzle we encountered in the earliest galaxies: time. Everything comes back to time. Astronomers understand how black holes can grow. They consume gas. They merge with other black holes. They gradually accumulate mass over immense periods. The process works perfectly well across billions of years. But Webb keeps finding objects that seem unwilling to wait. Ancient galaxies that became massive too quickly. Ancient black holes that grew too quickly. Ancient structures that appear surprisingly mature despite existing when the universe was still in its infancy. It is as though the early cosmos operated according to a more aggressive schedule. The question is why? Some researchers suspect that the first black holes may have formed differently than modern ones. Instead of growing from collapsing stars, perhaps gigantic clouds of gas collapsed directly into massive black holes. Others suggest that unusual conditions in the young universe allowed matter to accumulate far more efficiently than expected. There are even theories involving forms of dark matter that could have accelerated structure formation. At present, nobody knows. And that uncertainty is exactly what makes Webb's discoveries so important. The telescope is not simply answering questions, it is exposing new ones. One of the most fascinating aspects of black holes is their relationship with galaxies themselves. For many years, scientists assumed galaxies formed first, and black holes appeared later. Increasingly, evidence suggests the relationship may be more complicated. Black holes and galaxies seem almost intertwined. As galaxies grow, their central black holes grow. As black holes become active, they influence their galaxies. Powerful jets erupt from galactic centers. Radiation floods surrounding regions. Gas clouds are compressed or scattered. Star formation rates change. In some cases, black holes appear capable of regulating the evolution of entire galaxies. Imagine something smaller than our solar system influencing structures containing hundreds of billions of stars. The scale difference is almost absurd, yet nature seems perfectly comfortable operating this way. Webb's observations are helping astronomers study these relationships across cosmic history. By looking farther into the past than ever before, scientists can examine how galaxies and black holes evolved together over billions of years. The results suggest that their connection may be deeper than previously imagined, and black holes are not the only giants shaping the universe. As Webb continues surveying the cosmos, it frequently encounters structures so vast that individual galaxies become mere building blocks, clusters of galaxies, superclusters, cosmic webs stretching across unimaginable distances. One of the most striking examples is Pandora's cluster. At first glance, it appears to be a crowded region of space containing numerous galaxies. In reality, it is far more impressive than that. Pandora's cluster represents multiple galaxy clusters colliding and merging across hundreds of millions of light years. The combined mass is so enormous that it bends space itself. This effect, known as gravitational lensing, acts like a natural cosmic magnifying glass. Light traveling behind the cluster becomes distorted. Galaxies located even farther away are stretched, warped, and amplified. Thanks to this phenomenon, Webb can observe objects that would otherwise remain invisible. Nature itself becomes part of the telescope. Einstein predicted this effect more than a century ago. Today, Webb uses it routinely. The universe is helping us observe itself. And through these giant gravitational lenses, astronomers are finding some of the most distant and ancient galaxies ever detected. Again and again, everything connects. Black holes influence galaxies. Galaxies gather into clusters. Clusters distort space-time. Distorted space-time reveals even older galaxies. Every layer of the cosmos leads naturally to another. The deeper we look, the more interconnected reality appears. What once seemed like isolated celestial objects increasingly resemble parts of a single evolving system stretching across billions of years and trillions upon trillions of miles. And yet, perhaps the most surprising lesson emerging from Webb's observations is that complexity appears everywhere, not just in galaxies, not just in black holes, not just in planetary systems. Even the chemistry of the universe is proving richer than expected. Because while astronomers were studying these giant structures, Webb began detecting something else hidden within ancient galaxies: complex molecules, unexpected chemistry, the very ingredients that would one day become the foundation of life itself. And their discovery suggests that the universe may have started experimenting with complexity far earlier than anyone imagined. For much of the 20th century, astronomers viewed the early universe as a relatively simple place. The first stars formed, the first galaxies assembled, heavy elements gradually accumulated, complex chemistry emerged slowly over billions of years. At least, that was the expectation. Yet, as the James Webb Space Telescope continues looking deeper into cosmic history, that timeline is beginning to feel increasingly incomplete. Again and again, Webb is finding evidence that the young universe may have matured far faster than anyone anticipated. The same pattern that appeared with ancient galaxies and supermassive black holes is now appearing in chemistry itself. And if these observations hold true, they may force scientists to rethink how quickly complexity emerged after the Big Bang. One of Webb's most fascinating discoveries came from a galaxy located more than 12 billion light-years away. To put that distance into perspective, the light reaching the telescope today began its journey long before Earth existed. Entire mountain ranges on our planet had not yet formed. The Sun itself was still billions of years in the future. Yet hidden within that ancient galaxy, Webb detected something unexpected: complex carbon-based molecules, the same types of molecules commonly associated with soot, smoke, and organic chemistry here on Earth. The discovery surprised researchers because these compounds require a certain degree of chemical enrichment to form. Stars must first manufacture heavier elements. Those elements must then be dispersed into space. Complex molecules must subsequently assemble from those ingredients. The process was expected to take time, a lot of time. Instead, Webb found evidence that such chemistry was already present when the universe was still remarkably young. It was another reminder that cosmic evolution may have unfolded more rapidly than our models predict. And perhaps this shouldn't surprise us. After all, complexity seems to be one of the defining characteristics of the universe. Give gravity enough time, and it creates stars. Give stars enough time, and they create elements. Give elements enough time, and they create chemistry. Give chemistry enough time, and eventually, at least once that we know of, it creates life. What makes Webb's discoveries so intriguing is that they suggest some of these steps may have begun astonishingly early. The ingredients were appearing sooner. The structures were growing faster. The universe seemed eager to experiment. This raises a profound question. How common are the conditions that eventually lead to life? For centuries, humanity assumed Earth occupied a unique position in creation. Then astronomy revealed that Earth was merely one planet orbiting one ordinary star among hundreds of billions in a single galaxy. Later, astronomers discovered that our galaxy itself was only one among trillions. Now, Webb is helping us examine the environments surrounding distant worlds in unprecedented detail. And while it has not found life, it is beginning to identify some of the ingredients associated with habitability: water vapor, carbon dioxide, methane, complex organic molecules. These discoveries do not prove that life exists elsewhere, but they do demonstrate that the chemistry of life is not unique to Earth. The universe appears remarkably capable of producing the necessary building blocks. In a way, this changes how we view ourselves. For generations, people looked at the stars and saw distant points of light. Today, we increasingly see potential worlds, potential oceans, potential atmospheres, potential ecosystems, potential histories unfolding beneath alien skies. The night sky feels less empty than it once did, and Webb is accelerating that transformation. Its infrared instruments can analyze atmospheres with extraordinary precision. Tiny changes in starlight reveal the fingerprints of distant chemicals. Worlds that once existed merely as dots on a chart now possess weather systems, atmospheric compositions, and environmental characteristics. Some are scorching infernos, others are frozen wastelands. Some possess clouds of silicate particles, others may contain exotic atmospheric processes unlike anything found in our solar system. The sheer diversity is staggering, and it teaches us something important. Nature rarely repeats itself exactly. The universe does not seem interested in creating identical copies. Instead, it experiments, again and again. Different stars, different planets, different environments, different outcomes. This diversity extends beyond planets themselves. Even entire galaxies appear to evolve along different paths. Some become calm spiral systems, like the Milky Way. Others transform into giant elliptical structures containing trillions of stars. Some experience violent bursts of star formation. Others remain comparatively quiet for billions of years. Everywhere Webb looks, variety emerges. And yet, beneath that variety, certain patterns remain. Gravity continues gathering matter. Stars continue forging elements. Galaxies continue evolving. The same fundamental laws operate across the observable universe. It is almost as though complexity emerges naturally from simplicity. A few basic physical rules give rise to structures of astonishing richness. This realization carries a strangely philosophical weight. Everything we see around us, every mountain, ocean, cloud, city, and living creature, ultimately emerged from simple physical processes operating over immense spans of time. The universe did not begin with complexity. It grew into complexity, slowly, patiently, relentlessly. And perhaps nowhere is this process more visible than in the regions where stars are still being born today. Because while Webb has shown us ancient chemistry and distant planetary systems, it has also revealed something equally remarkable: the ongoing creation of entirely new stars. Across the Milky Way and beyond, stellar nurseries continue transforming clouds of gas into blazing suns. Future solar systems are forming right now. Future planets are assembling right now. Perhaps even future civilizations are beginning their stories right now. The universe is not merely a relic of the past. It is still creating, still evolving, still building. And as Webb turns its gaze towards some of the most spectacular stellar nurseries ever observed, it reveals a cosmos that is far more alive, dynamic, and creative than we once imagined. One of the most surprising lessons from the James Webb Space Telescope is that the universe is not a static place. It is tempting to think of the cosmos as something ancient and finished. We look at the stars and imagine them frozen in place. We look at galaxies and assume they have always existed exactly as they appear today. But the deeper Webb looks, the more obvious it becomes that the universe is still under construction. Everywhere we turn, things are being built. Stars are being born. Planets are assembling. Galaxies are evolving. Entire regions of space are undergoing transformations that will continue long after humanity itself is gone. This ongoing creativity becomes especially clear inside stellar nurseries. These immense clouds of gas and dust are among the most beautiful structures ever observed. But beauty is only part of the story. What makes them truly remarkable is that they are factories. Not factories built from steel and concrete, but factories operating on scales so vast that light itself requires centuries to cross them. The Tarantula Nebula is one of the finest examples. Located roughly 160,000 light-years away in the Large Magellanic Cloud, it is the most active star-forming region in our local neighborhood of galaxies. Earlier telescopes revealed portions of its structure, but Webb transformed our understanding completely. Suddenly, thousands of previously hidden stars appeared. Dark regions that once seemed empty became crowded with activity. Dense clouds concealed entire populations of infant stars. Intricate filaments stretched across space like glowing rivers of cosmic dust. The image almost feels alive, and in many ways, it is. Inside these regions, gravity continuously pulls matter together. Gas clouds collapse, temperatures rise, new stars ignite. Their radiation then begins sculpting the surrounding environment, triggering new waves of star formation while simultaneously destroying the very clouds that created them. Creation and destruction happen side by side. The process never truly stops. What Webb has shown with extraordinary clarity is that star formation is not neat and orderly. It is turbulent, chaotic, dynamic. Massive stars blast powerful winds into surrounding clouds. Shock waves ripple through gas. Jets erupt from newborn stellar systems. Dust and radiation collide in an endless cosmic dance. And from this apparent chaos emerges structure. This is one of the universe's most fascinating tendencies. Again and again, complexity emerges from disorder. The same principle shaped galaxies. The same principle shaped planetary systems. The same principle ultimately shaped life. Order is not imposed upon the universe from outside. It emerges naturally from the interactions of matter, energy, and time. Webb's images make this reality impossible to ignore. Perhaps nowhere is this more evident than in the famous pillars of creation. Many people recognize these towering structures from photographs taken by the Hubble Space Telescope. For decades, they have been among the most iconic images in astronomy. Yet when Webb observed them, something remarkable happened. The pillars changed. Not physically, of course. Our understanding of them changed. Hubble showed dramatic columns of gas and dust reaching across space like cosmic monuments. Webb revealed what was hidden inside them: thousands of stars, newborn stellar systems, regions actively participating in the creation of future generations of planets. The pillars are not merely beautiful objects, they are nurseries. Inside them, gravity continues its slow work, gathering material that may one day become entirely new worlds. The realization is strangely moving. Somewhere inside those distant clouds, planets may currently be forming. Perhaps rocky worlds similar to Earth. Perhaps giant gas planets larger than Jupiter. Perhaps systems completely unlike anything humanity has ever imagined. The universe is continually producing possibilities, and Webb is allowing us to witness that process directly. Yet even these magnificent nurseries represent only one stage of a much larger cycle. Stars are born, stars live, stars die, and their deaths reshape the cosmos just as profoundly as their births. Massive stars end their lives in supernova explosions so powerful that they briefly outshine entire galaxies. These explosions scatter heavy elements across space, enriching future generations of stars and planets. Without supernova, there would be no rocky planets, no oceans, no biology, no observers. The deaths of ancient stars made our existence possible. This cosmic recycling process has been occurring for billions of years, generation after generation. Stars creating elements, stars distributing elements, new stars forming from enriched material, new planets emerging around those stars. The universe behaves almost like an ecosystem operating on incomprehensible scales. Nothing is wasted. Matter changes form. Energy changes form. But the story continues. And as Webb studies these processes, another realization begins to emerge. The universe is not only larger than we imagined, it may also be older in spirit than we imagined. Again and again, Webb finds evidence that mature structures appeared surprisingly early. Massive galaxies, giant black holes, complex chemistry, rich stellar environments. The cosmos seems to have become sophisticated very quickly after the Big Bang, which brings us back to one of the deepest mysteries of all. If galaxies evolved faster than expected, if black holes grew faster than expected, if chemistry became complex earlier than expected, then perhaps our broader picture of cosmic evolution is still incomplete. Perhaps there are chapters of the story we have not yet understood. And as Webb continues looking farther into space and deeper into time, it keeps encountering clues that point toward an even bigger mystery. A mystery not about planets, not about stars, not even about galaxies, but about the universe itself. Because hidden behind everything Webb observes lies an invisible framework shaping the evolution of the cosmos, something that cannot be seen directly, something that appears to outweigh all the stars and galaxies combined, something that may ultimately determine the fate of the universe. Dark matter, dark energy, the unseen forces governing almost everything. For thousands of years, humanity believed that what we could see was all that existed. The stars, the moon, the planets, the glowing band of the Milky Way stretching across the night sky. Even after telescopes revealed countless galaxies beyond our own, the assumption remained largely the same. We simply thought the universe was bigger than we had imagined. But over the last century, astronomers have uncovered a disturbing possibility. Most of the universe may be invisible, not hidden behind clouds, not too distant to observe, invisible by its very nature. As the James Webb Space Telescope peers deeper into cosmic history, it is not only revealing galaxies and stars, it is also helping us understand the unseen framework that governs their existence. Because every galaxy Webb observes raises the same question. Why does it hold together? At first glance, gravity seems like an obvious answer. Stars orbit the centers of galaxies. Galaxies gather into clusters. Massive structures form across the cosmos. Gravity appears to explain everything. Yet when astronomers actually measured these systems, something didn't add up. Galaxies were rotating too quickly. Far too quickly. According to the visible matter they contained, many should have torn themselves apart billions of years ago. Instead, they remained intact. Something else was providing additional gravity, something invisible, something that could not be directly detected. Scientists eventually gave this mysterious substance a name: dark matter. The name sounds dramatic, but in reality, it reflects our ignorance more than our understanding. We do not know what dark matter is. We only know what it does. It bends light. It influences gravity. It helps shape galaxies. Without it, the large-scale structure of the universe would look completely different. In fact, current estimates suggest that ordinary matter, the matter making up stars, planets, trees, oceans, and human beings, accounts for only a tiny fraction of the universe. Everything you have ever touched, everything you have ever seen, every mountain, every ocean, every city, every living creature, combined, they represent only a small percentage of cosmic reality. The rest is something else. And Webb is helping scientists investigate its role in the early universe. This is one reason the discovery of massive ancient galaxies caused such excitement. Those galaxies did not simply challenge ideas about star formation. They challenge ideas about structure formation itself. According to current models, dark matter acted as a kind of cosmic scaffolding after the Big Bang. Invisible concentrations of dark matter created gravitational wells that attracted ordinary matter. Gas flowed into these regions, stars formed, galaxies emerged. In this picture, dark matter helped build the universe. But if galaxies formed faster than expected, then perhaps the role of dark matter is more complicated than we thought. Perhaps the scaffolding was assembled differently. Perhaps additional processes were involved. Or perhaps there are aspects of dark matter we have not yet discovered. Webb is not directly observing dark matter. No telescope can. But by studying the visible structures it helped create, astronomers can begin reconstructing its influence. It is a little like studying the wind by watching trees move. You never see the force itself. You see its effects. And everywhere Webb looks, the effects are unmistakable. Yet dark matter is only half the mystery, because as strange as it may sound, the universe contains something even more puzzling, something that appears to be pushing the cosmos apart, something that may ultimately determine how everything ends: dark energy. The story begins with one of the most surprising discoveries in scientific history. For much of the 20th century, astronomers assumed the expansion of the universe should be slowing down. Gravity pulls matter together. Galaxies attract one another. Over time, expansion should gradually weaken. That seemed reasonable. Then observations revealed the exact opposite. The expansion of the universe is accelerating. Galaxies are not merely moving apart. They are moving apart faster and faster. Some unknown force appears to be driving the acceleration. Scientists called it dark energy. And once again, the name is really a placeholder for our ignorance. Nobody knows exactly what dark energy is. Yet according to current measurements, it makes up the majority of the universe. Think about that for a moment. The stars, the planets, the galaxies, the black holes, everything Webb has photographed, everything humanity has ever observed, represents only a minority of cosmic reality. Most of the universe consists of phenomena we still do not fully understand. It is a humbling realization. The more we learn, the more obvious our ignorance becomes. And perhaps that is one of Webb's greatest achievements, not simply providing answers, but revealing how many questions remain. Every major discovery made by the telescope seems to point toward larger mysteries. The earliest galaxies challenge models of cosmic evolution. Ancient black holes challenge models of growth. Complex chemistry challenges timelines for structure formation. And behind all of it stand dark matter and dark energy, silently shaping events across billions of years. There is something almost poetic about this. The universe appears far stranger than the human mind initially expected. Not because reality is chaotic, but because reality is deeper. Every layer we uncover reveals another beneath it. Every answer opens new questions. Every discovery expands the frontier. Perhaps that is why the James Webb Space Telescope feels so different from previous observatories. It is not simply showing us new objects. It is exposing entirely new levels of reality. The telescope began by searching for the first galaxies. In doing so, it has led us toward questions about the invisible architecture of existence itself. And yet, as profound as these mysteries may be, they ultimately lead toward an even larger question. A question that sits quietly behind every image Webb captures. A question that has followed humanity since the first people looked up at the stars. What does all of this mean? What are we supposed to make of a universe so vast, so ancient, and so mysterious? To answer that, we need to step back from the individual discoveries, the galaxies, the planets, the nebulae, the black holes, the chemistry, the invisible forces, and look at the bigger picture. Because when viewed together, Webb's discoveries tell a story far greater than any single observation. They tell the story of a universe becoming aware of itself. If you zoom in on any single James Webb image, you will find a story. A galaxy forming in the early universe, a newborn star emerging from a cloud of dust, a strange planet orbiting a distant sun, a black hole feeding in the darkness. Each discovery is fascinating on its own. Each could fill entire books and occupy generations of researchers. Yet perhaps the most remarkable thing about Webb's mission is not any individual object it has found. It is the larger picture that emerges when all of those discoveries are viewed together. Because taken together, they reveal something extraordinary. A universe that has been evolving for nearly 14 billion years. A universe that began in simplicity and gradually grew more complex. A universe that transformed energy into matter, matter into stars, stars into planets, and somehow, eventually, planets into observers. The story begins with the Big Bang, a hot, dense state unlike anything we experience today. There were no galaxies, no stars, no planets, no life, just an expanding sea of energy and possibility. Then gravity began its work. Tiny fluctuations grew larger, clouds formed, the first stars ignited, the first galaxies assembled, heavy elements emerged, planets appeared, life became possible, and eventually, on at least one small world orbiting an ordinary star, something remarkable happened. Matter began asking questions about itself. That is ultimately what every telescope represents, a way for the universe to investigate its own existence. When you think about it, the idea is almost absurd. The atoms inside your body were forged in ancient stars. Those stars were assembled from matter created shortly after the Big Bang. The same physical laws that govern distant galaxies govern your own existence. The universe is not something separate from us. We are one of its products, one of its consequences, one of its experiments. And now, through machines like Webb, we have become one of its observers. For billions of years, galaxies evolved without witnesses. Stars were born without witnesses. Black holes grew without witnesses. Entire cosmic epochs passed in complete silence. Then, relatively recently, a species emerged on a small rocky planet and began wondering where it came from. That species learned to build telescopes, first simple ones, then larger ones, then observatories capable of leaving the planet itself. And finally, after centuries of scientific progress, it built the James Webb Space Telescope, a machine capable of seeing the oldest light in existence, a machine capable of reading messages sent billions of years before humanity appeared, a machine capable of revealing chapters of cosmic history that had remained hidden since the beginning of time. The deeper Webb looks, the more astonishing the story becomes. Ancient galaxies that seem too large, black holes that seem too old, complex chemistry appearing earlier than expected, planetary systems emerging inside stellar nurseries, invisible forces shaping the evolution of everything we see. Every discovery reminds us that reality is richer than our assumptions. The universe is under no obligation to match our expectations. And perhaps that is the most valuable lesson of all. Science is often portrayed as a collection of answers. In reality, it is a process of refining questions. The more accurately we observe the cosmos, the more mysteries we uncover. Webb has not solved astronomy. It has expanded it. It has shown us that even after centuries of observation, the universe remains filled with surprises. And that is wonderful. Because a universe with no mysteries would be a very small universe indeed. Instead, we find ourselves living inside a cosmos that continues to reveal new layers of complexity the deeper we look. There is something deeply hopeful about that. Every generation inherits unanswered questions. Every generation pushes the frontier slightly farther, and every generation leaves new mysteries behind for those who follow. The people who first mapped the stars could never have imagined Webb. The people who built Webb could never fully predict what it would discover. And the discoveries being made today will undoubtedly inspire even more powerful observatories in the future. Perhaps one day humanity will directly image Earth-like planets. Perhaps we will find signs of life elsewhere. Perhaps we will finally understand dark matter. Perhaps we will uncover entirely new laws of physics. Or perhaps the greatest discoveries remain beyond our imagination altogether. History suggests that the universe still has many surprises left, and that may be the most exciting possibility of all. Because despite everything Webb has revealed, we are still standing at the beginning. The observable universe contains trillions of galaxies. Each galaxy contains billions or even hundreds of billions of stars. Many of those stars host planets. The scale is almost impossible to comprehend. Yet for the first time in history, humanity possesses an instrument capable of exploring this vast cosmic ocean with unprecedented clarity. The James Webb Space Telescope is not merely showing us distant objects, it is helping us understand our place within a much larger story, a story stretching from the first moments after the Big Bang to the present day, a story of creation, transformation, complexity, and discovery, a story that ultimately led to us. And perhaps that is why these images resonate so deeply. When we look into the depths of space, we are not simply observing distant galaxies. We are looking at our own origins. We are witnessing the events that made our existence possible. We are reading the earliest chapters of a story that is still being written. And somewhere tonight, as Webb quietly drifts more than 1 million miles from Earth, its mirrors are collecting photons that have traveled across billions of years of cosmic history. Ancient messengers from a time before stars like our Sun existed. Ancient messengers carrying new secrets. Ancient messengers reminding us that the universe remains far larger, stranger, and more beautiful than we have yet imagined. And as long as there are mysteries waiting in the darkness, we will keep looking. Because every answer leads to another question. Every discovery opens another door. And beyond every horizon lies another one waiting to be explored. If you enjoyed this journey through the deepest reaches of space and time, make sure to subscribe to Epic Space News. There is still so much more to discover, and together we'll continue exploring the universe, one mystery at a time. Until next time, keep looking up.